This is Lesson 5 of Module 4 on vectors. Here we're going to talk about vector mathematics, how we can apply what we know about vector components in particular in order to perform analytical mathematical operations with vectors, basically addition and subtraction, multiplication, using our calculator and using numerical values rather than trying to draw pictures that are subject to artistic limitations. So the process that we're going to use when we have vectors is to break our vectors into components. We said that you have vectors that are in all different directions, and so you can't really add them or subtract them easily because you have to account for those different directions, and you have to account for that using the tip-to-tail method, for example. But if you break vectors into their components, then essentially you're breaking those vectors into a bunch of purely horizontal and purely vertical vectors. And when you have horizontal and vertical vectors, the horizontal vectors are all aligned with each other, and so they all are in the same direction. And so you don't have to worry about accounting for their directions. When they're all in the same direction, you can simply add and subtract all of these horizontal vectors together. And the same thing with the vertical vectors. The vertical vectors are all aligned with each other, and so that allows us to relax the rules that we have to follow in order to account for those directions. So we break them into components, and once we have components, we'll do all of our calculations, all of our algebra, just as we normally would, looking at each dimension independently. We've already looked at one-dimensional motion, and so in the x direction and the y direction and z direction, those are all one-dimensional systems that we can consider separately. Once we have dealt with each dimension independently, then we can recombine the components to find the magnitude and the direction of the resultant of whatever it is that we were trying to solve for. So basically all of the same operations that we've seen before. We've talked about position and displacement and velocity and acceleration. We talked about doing integrals and derivatives, all of that. Basically, if you had one three-dimensional vector, you break that up into three one-dimensional calculations, and all of the other math that we've talked about, we can apply that to each component in each direction separately. So for example, if we were going to add two vectors, a plus b was to give us some vector c. Here is vector a, there's vector b, and together it gives us vector c. Notice that vector c starts where a starts, it ends where b ends, and we've used the tip-to-tail method to add those two vectors. But vector a itself has x and y components. Vector b itself has x and y components. And so we see here that if you take the x component of a plus the x component of b, together gives us the x component of c. If we look at the y component of a plus the y component of b, that gives us the y component of c. So we can simply, when we had to use the tip-to-tail method to add them as vectors, we simply add them numerically as components when we have the x and the y components separated. Here we've sketched this in two dimensions. If we had a z direction, we could simply add the z components as well. If we're going to subtract two vectors, we've seen how to subtract two vectors, but if we break them into components, we can simply subtract the components to find the difference between those two vectors. Furthermore, if we want to multiply a vector and a scalar by components, if we multiply a vector times a scalar, we're going to simply multiply each component by that same scalar. So we talked before about how if I take vector A and I multiply it by 2, I have two vectors that point along parallel lines, where this vector should be twice as long as that one. So here we've multiplied the magnitude by 2. But if we multiply the magnitude by 2 and we keep the angle the same, the direction the same, then if you use your sines and cosines to find the components, you would expect to find that the x and y components would each be twice as long as their original value. So we've multiplied each of those components by 2, which makes sense. These are similar triangles, and so their sides should be proportional to one another. If we divided by a scalar, recall that dividing by a scalar would be like dividing by 2. We could multiply by half. That would give us a vector that's half as long as the original, and all of the components would be half as much as the original as well.